most important type of accelerations that we're going to deal with in 2 dimensions is constant acceleration. So constant acceleration in 2D. And in a lot of ways, it's very similar to constant acceleration in 1D. So what this means is that acceleration is a function of time is just equal to ax, ay, and those 2 things are constants. So now from this, let's derive an expression for the velocity as a function of time. Given that at time equals 0, the velocity is equal to v0. Okay, where these are, again, these are just numbers, constants. Well, to do that, you have to integrate, right? The velocity vector is the integral of the acceleration vector with respect to time. So what do you get if you integrate a constant with respect to time? You get axt plus some constant c1, and you get ayt plus some constant c2. And now to find c1 and c2, we'll use those boundary conditions. So the boundary condition for the x component says if you plug 0 in for t for this function, the x component of v is v0x. So v0x is equal to this number ax times 0 plus c1. And so c1 is equal to v0x. And in other words, vx as a function of time then is axt plus v0x. Usually you see it written in the other order, v0x plus axt. And you probably recognize the form of that equation. And then the boundary condition for y works the same way. v0y is equal to ay times 0 plus c2. So c2 is equal to v0y. And so vy is a function of time. Comes out the same way. V is equal to v0y plus ay times t. And what these tell you together is that the velocity vector as a function of time is equal to the v0 vector plus the a vector times t. And now you can integrate that to come up with the position vector. Let's see. So now we want to derive position vector as a function of time, given that when time is equal to 0, the position is p0x, p0y. And it works out similarly. I won't go through all the steps, but there's a homework assignment problem where you're supposed to do this. So what you get is that position vector as a function of time is equal to p0 vector plus v0 vector times t plus 1/2 times the acceleration vector times t squared. And now if you combine the function for vy and the function for v and the function for p, you can come up with that third pair of equations that looks like our third constant of acceleration equation in 1D. Okay, and we can think of this as giving us 6 independent equations. So I'm going to skip that last set of equations. But we get 6 independent equations. For constant acceleration in 2D. And those are Vx is equal to V0x plus AXT. And then the y version of that one, Vy, is equal to V0y plus AYT. And now we'll go on to the 2 position equations. The first one says Px is equal to P0x plus V0xt plus 1/2 AX t squared. And the second one says Py is equal to P0y plus V0yt plus 1/2 AY t squared. And then the third pair of equations says 2AX times the quantity Px minus P0x is equal to Vx squared minus V0x squared. And its companion, the y component equation, says 2AY times the quantity Py minus P0y is equal to Vy squared minus V0y squared. Okay, well, to solve problems with these, now there's a whole bunch more variables you have to keep track of. Before there was just T, A, P0P, V0V. Now for all of those except time, there's 2 components, right? So the possible variables that you're dealing with are now T, AX and AY, P0x and P0y, Px and Py, V0x and V0y, and Vx and Vy. So we went from dealing with 6 total variables to, I think there's 11 here now. I want to give you a handful of things to look for that are going to come up pretty often. And then we'll just go through a bunch of examples. And you'll see that when I do problems, I do them really with the same exact process I did in 1D. It's just more equations, more variables. Okay. But here are 4, I think, things that you should keep in mind. So notice. Okay, the first one is only T appears in both X and Y equations. Well, it doesn't appear at all in those last two because time doesn't appear in that form. But like if you look at the velocity equations and the position equations, no X's are in the Y equations, no Y's are in the X equations. The only thing that you see in both is time. And what that means, practically speaking, for using these is, so if no equation works, remember in 1D that would happen sometimes, no equation would work, and then you'd look for either acceleration or time, most likely. It's almost always going to be time that you want to solve for in order to then go back and try to solve for the variable that's asked for. Okay. And that's because, you know, so the way it works is like, say you're trying to solve for the final Y velocity, okay? But there's no equation that works to solve for the final Y velocity. Well, maybe you can use the X equation here to solve for time, and then that'll let you use this one because the time there is the same as the time there. Okay, that's a pretty common flow for these. And the first example I'm going to do is going to work that way. And the last 3 are all related to velocities. The second one is that we're often going to have to get a velocity vector get the velocity vector components from a speed and an angle. So like, for example, if you know that an object is launched at 20 meters per second at an angle of 30 degrees above horizontal, then that velocity, so say this represents time equals 0, then our initial velocity vector is going to be 20 times the cosine of 30 degrees, 20 times the sine of 30 degrees. Okay, that's going to be really common. So the problem will say like, okay, this ball is thrown from a height of 2 meters at an angle 20 degrees below horizontal or whatever, and with a given speed, and you use that to find those initial velocity components. The third thing is at the highest point in an object's flight. Well, in 1D, comma, in 1D, its highest point was defined by the velocity equal to 0, right? If you throw something up in the air, then right before it starts to come back, its velocity is equal to 0, okay? So your first thought, you might think, okay, maybe the velocity vector is equal to 0, but that's not quite right. And to make sense out of that, imagine this. I'll fill this in, give yourself a line here below, but okay, so ask yourself if this seems like a good idea. Okay, so this is like Tory Hunter or someone. Actually, it looks like a gorilla or something. But okay, so ask yourself if you want to do this. Figure out right where, so this, some baseball player is throwing the ball to the home plate from center field. And you figure out exactly where the ball is going to reach the highest point. You set up a step ladder and stand on the top. It says that's not a step, but ignore that and stand up on the top. And since you're right where the ball is at its highest point, what you would expect is this ball to come up, slow down, and just nuzzle gently against the back of your head there. And then you can just take it and, you know, free baseball, you know. But obviously, that would be a terrible idea. This ball is still going really, really fast. And okay, so don't do this. So when the ball gets to its highest point, what happens is the y component of the velocity is equal to 0, or the vertical component, okay? But the horizontal speed is still the same as it was at the start. So if this ball is thrown at this angle at 100 degrees, if you ignore air resistance, it's still going 100 miles an hour is what I meant. It's still going 90 some miles an hour there. It just doesn't have any vertical component to the velocity, okay? So the vertical component of the velocity is 0. Usually, I'm going to recommend that you choose your y-axis to point up. So this usually means Vy is equal to 0. Okay, so the horizontal component is not 0. Any questions about that? And then the last thing to keep in mind for these is if an object is dropped, this works just the way it did in 1D. The velocity vector at the release is the velocity vector of whatever it's dropped from. So if you take a balloon, you know, something with, it's very affected by air resistance if you drop it or whatever. But you take it in your car and you drive 55 miles an hour in your car and you hold it out the window. There's enough air resistance that it would be hard to hold your arm out there while you're holding it. But if you hold it out there, the instant you let go of it, that balloon is moving 55 miles an hour horizontally. A fraction of a second later, it's going way slower than that. But at the instant you let it go, the velocity is the velocity of whatever it's dropped from. Okay. All right, any questions about those? Keep those 4 things in mind as you go through problems. Those are going to be useful pretty often. All right, so let's do an example. So let's say a shot putter releases the shot at an angle of 45 degrees above the horizontal. With a speed of 12 meters per second. The height at release is 1.8 meters. How far is the throw? Okay. So it's released at an angle of 45 degrees above horizontal with an initial speed of 12 meters per second. So this is 45 degrees. And this height is 1.8 meters. And the flight is like that. And we want to figure out this distance. Okay, so in one-dimensional motion, what were the 4 things that we had to choose before we started doing a calculation?
Zero position, positive direction, and the position of time.
Yep, so in 1D, we chose a time equals 0, a time t, a 0 position, and a positive direction. What's the 2-dimensional equivalent of choosing time equals 0? Trick question. Time equals 0 is still the same if we're talking about time. So the 2D equivalent of choosing time equals 0 is choosing a time equals 0 instant again. It's exactly the same thing. Same with t. So choosing a time t, those two are exactly the same. Now, this is the one that you were thinking of. What's the 2-dimensional equivalent of a 0 position? That's choosing a location for the origin. Okay, and what's the 2-dimensional equivalent of choosing the positive direction? That's choosing the orientation of the coordinate axes. So I'll call that a coordinate system orientation. And just like we did in one dimension, we're going to choose time equals 0 and time t based on where we have information and where we want information. So our time equals 0 here is going to be at the instant it's released. Our time t is going to be when it hits the ground. And you have more flexibility with the origin location and the coordinate system orientation. But what I'm usually going to do in projectile motion problems is I'm going to put the origin at the lowest point in the problem. That's the ground usually, or the water if it's going to hit water or whatever, right underneath where the object is at time equals 0. And I'm going to choose the y-axis up. Okay, so my x-axis is that way, my y-axis is that way. The origin is on the ground right below where it was thrown from. So these two are shown. And now we can go through the list of variables, think about which ones we know. So I'm going to write the variables out like this. There's t. Acceleration is a vector. P0 is a vector. That's the position at time 0. P is a vector. V0 is a vector. And V is a vector. Okay, and we'll see what we know about these. Do we know how long it takes for the object to hit the ground? No. If we need to later, that's something we can probably calculate, but we don't know it off the bat. Do we know A? That's right. So in 1D and 2D, what gravity doesn't change. Gravity always accelerates things straight down at 9.81 meters per second squared. Now down it's a vector, so you give it as components. So in this coordinate system, that's 0, negative 9.81. If you chose a different coordinate system, it would be different, you know. But so the acceleration is 0, negative 9.81 meters per second squared. Now P0, that's the coordinates of the shot when time is equal to 0. So what are the coordinates of this point? 0, positive 1.8, yep. What about the position at time t when it hits the ground? Do we know anything about the position there? The y component is 0. We don't know anything about x. That's what we're trying to find. So py is 0, and px is what we want. Do we know anything about the velocity at time equals 0? It's 12 meters per second at this angle. And so if you put this down at the origin and find the counterclockwise angle from the x-axis to the vector, that would be 12 times cosine and sine of 45. So 12 times cosine of 45, 12 times sine of 45. Okay, it's the same for sine. And then meters per second, so that's that. And do we know anything about the velocity at time t? Well, the official answer is no, we don't know anything at time t. We don't know that it's 0. That's an easy mistake to make, so be sure you don't do that. Remember that these equations only work for constant acceleration, and so they only work while this object is in its projectile motion. The instant it touches the ground does stop something about it at least, but as soon as it touches the ground, these equations don't work anymore. Okay, so what we really are talking about here is the velocity the instant before it hits the ground. And the official position is that we don't know anything about that velocity at that instant, okay? But I'm going to tell you something off the record, okay? This doesn't go into the calculations. But off the record, look at that acceleration component. Remember, acceleration tells you how velocity is changing, okay? Well, that means that the y component of the velocity is changing over time, because this is non-zero. But the x component of the velocity isn't changing, okay? So in any problem like this, where your y-axis is pointing up and your x-axis is horizontal, the x component is going to stay the same for any time, okay? But the reason that I said that's off the record is because if you put that x component in here as known, it's going to look like equations are going to work that in the end are just going to, everything's going to cancel out. It won't give you anything helpful. So we'll always just assume that we don't know that, okay? Because remember what acceleration is how quickly the velocity is changing. And so if you have 0 acceleration, velocity isn't changing. And one of these components, acceleration isn't 0, but the x component is 0. So that means the x component of velocity is going to stay the same the whole time, which also sort of explains what I was saying about standing on that ladder and getting hit in the head with a baseball. So when that ball's thrown, it has a x component of 90 miles an hour and a y component of 10 miles per hour. When it hits you on top of the ladder, that component of 10 miles per hour is gone, but that 90 is still the same. Okay, so we're going to assume we don't know this for now. So what equations work out of those? Are there any equations that are going to let us calculate px? Well, we know, so we're looking for px. Well, we know that these don't work because there's no px in it. You can't solve for something that's not there. And we know the two y equations don't work because you can't solve for an x thing with a y equation. It's not there. So the only two candidates we have left are this one and this one, these two x equations. We don't know t, so this one isn't going to work. And we don't know vx. That's right. And so nothing works. Oh. We know p0x, but we don't know px. Oh, right. If it was asking for vx, then we could use our off-the-record knowledge and just write that down. Yeah. So none of them work. So what are we going to do now? Yeah, so that means that we want to solve for t first. Okay, so is there an equation that works for t? Yep, perfect. The third equation is going to work. You know these two don't work because there's no t in those. You don't know anything about v, so those two aren't going to work. You don't know px, so this one won't work, but the second one here will, the second position equation. So we're going to use py is equal to p0y plus v0y t plus 1/2 ay t squared. And we get that 0 is equal to 1.8 plus, what was that, 8.48? 8.48 t plus 1/2 times negative 9.81 is minus 4.905 t squared. So yeah, how are we going to solve that? That's right. So this is A, this is B, this is C. Anybody have a quadratic programmed into your calculator?
I have two answers, -0.19 and then 1.919.
Okay, so 0, -0.9, and then 1.91, did you say? Or 92? Okay. So those are the two roots of this quadratic equation. Which of those two do we want? Yeah, we're never using negative times, so this is the one we want. And now that we have t, now we can plug that into this equation. We're looking for px. So px is equal to p0x was 0, v0x was 8.48 times the time we just calculated. Ax is 0. And so what do you get for 8.48 times 1.92? So 16.28 meters, right around 40 feet somewhere.